Okay, this is roughly where I left you off last time. We were talking about modeling structure and how modeling behavior goes sort of hand in hand with that. You, on one side, want to do a bit of structural modeling because you want to have your domain model, have an idea of that at least before you start doing behavioral modeling, simply because the idea with object-oriented programming is that you want to mimic the reality as much as possible. So if you see that there are concepts in the real world, you would like to see an equivalent match to a class or an object in your code. And if you haven't done your study of the real world in your domain model, then you don't really know what classes you can start or use in your when you do your class diagrams and when you do your class design. Having said that, of course, there are situations where you will need to, first of all, as you do your behavioral modeling, as you do anything in design, you will learn more, which means that you will go back and you might add new concepts to your domain model. You may break apart a concept that you have into several smaller concepts. You might make an attribute into a concept. You might make a concept into an attribute and so on as you learn more, and that's natural. The other part is that you probably will come to situations where you need a certain class in order to make the software work, but there is no real equivalent of that in the real world. You will want to have, for example, if you have many items of a particular type in the real world, you might want to have a container for those in your source code, even if there is no such container in the real world. So there you would simply invent a class to be a container, even if you can't really find it in your domain model. So of course you can add things when you do your behavioral modeling, your dynamic modeling. That's your license as software designers. You take decisions on what is needed. And the point is that if we start with what we have in the domain model, we at least try to stick as close as possible to the real world. And when we're looking for what object should we assign responsibility for something, well, let's start by looking in the domain model and see if we can't find anything that fits there. And that way we have this closer mapping between the real world and the software system that we build. But as we go along, we will do a bit of behavioral modeling, and then we will update our structural models, and then we might add a bit more into our structural models, and that will mean that we can go back and revise our behavioral models. Once we're done, we might take a step back and we might apply a design pattern or one of the grasp patterns from the course book. And we can do that either by looking at the behavioral models, or we can look at the class diagrams, and we can see that we need a particular design pattern there, or a grasp pattern would make things clearer. And that of course means that we would have to go back and revise our behavioral models again. So we do these two activities very much hand in hand. So sorry, the first step of doing behavioral modeling is that we start with our use cases, as always, and we try to look at what happens in this use case that actually causes the system to, or requests a response from the system. And the way we see this is that the use case is it's written in natural language. It describes an interaction between actors and the system, and we do this as well as against the system as a whole. But what we want to do now is we want to see that the system is actually built up of at least two parts here. We have the system itself, the actual domain, problem domain that we build up, and we have a graphical user interface on top. I say graphical, it doesn't have to be graphical, it can be text-based as well, but we have a user interface on top. But what we want to do is that we want to separate these, and we want to see that whatever we do in the use case, we probably do it against our user interface, and then that generates system calls down to the business logic. And those method calls or system events, which we might call them, those method calls are what we want to extract from our use cases. You will do it as in the form of just listing the system events, list the method calls that are generated out of the use case. If you want to be a bit more fancy, you will do a system sequence diagram, which is essentially just a list that we have the actor, we have the system, and we have the method calls that are generated, and we have whatever the system returns, how the system responds to each system event. We will get a one-to-one mapping then. We will have one use case and one system sequence diagram. So for every use case, there will be one system sequence diagram. And then we will do one interaction diagram, that's the next step, for each system event. So each system event will have one interaction diagram where we try to look at inside the system. What objects do we need? How do we need them to collaborate so that we can respond with whatever we promised in the system sequence diagram so that we satisfy the use case. So let's use this as an example and see how we can extract these system events. The first step, this is from the point of sale system in the course book. The first step is that we arrive at the checkout. We have some items we want to purchase. We have a liter of milk and some bananas or whatever. We record the identifier from each item. So there's a barcode on each item. This is something that we do against the system, right? We send the barcode into the system and say that here's an item that we want to add to the current sale. And the system does a few things here. It decides the price of the item, adds it to a running sale transaction, and presents a description and the price of the current item. So this is the response to the system event that we want to record an identifier. Step 4 here, once we're done, we say that we tell the system that we are done. Entry complete or whatever. And then the system responds by calculating the total and how much the customer should pay. Point 6, the cashier tells the customer the total. This doesn't generate any system events here. The customer gives cash to the cashier. Still no system events. This is an interaction between the cashier and the customer. The system isn't involved in this. But the next step is that the cashier tells the system that I received cash, 500 crowns or whatever. And then the system should say that, well, if you got 500 crowns and the items that you was purchased cost so and so much, you should give this much in return. And it might open the till so you can take the money out as well. At the same time, it will also print a receipt because it's got all the information to do that. And those two things, 9 and 10, are a response to the system event that I received cash, payment by cash, and then how much money or how much cash was paid. So the cashier deposits the cash and extracts the balance from the till and then closes the till. And closing the till is a signal to say sale complete. And then the system logs this, updates the stock in the warehouse and so on. And then the cashier gives a printed receipt to the customer together with the balance. This doesn't involve the system. This is something between the cashier and the customer. And the customer leaves with the items and a receipt. Still no interaction with the system. So what did we get here? We got enter item. We might have some start sale or something like that as well, but enter item is the first one that we really see here. enter item, sale complete, pay by cash, and complete finish sale or whatever. Entry complete perhaps is a better word for this one. Entry complete and sale complete. These are methods calls. As I said, the user interface, we try to remove the user interface and we try to see what API do we have? Do we need to have? What programming interface do we need to have with the business logic part of the system? So these are method calls. What else is there to say about this? This is yep, we can skip ahead a bit. So as I said, for these system events, we can express them in a system sequence diagram, which is just a special case of a sequence diagram. So I'll be focusing on a sequence diagram instead. What we do in the sequence diagram is that we should actually, as I said, we should have one sequence diagram for each system event. So this should actually be two sequence diagrams. I just included both of them in the same picture because I was lazy. So there's one sequence diagram for start new sale up here, and there's another sequence diagram for enter item. But those are the two first system events from that use case. We see that there's an arrow pointing towards one of the objects. So these are objects, the yellow boxes. Each box is one object. And then we have a lifeline going down. And on that lifeline, we start calling methods on the object. So we call the method start new sale on the POS object. This starts the function. So this little red rectangle here is the extent of that function or method. So start new sale starts here and it ends here, and within the scope of that method, we create an object of type sale and we put it in a variable called current. Was there a question there, or? Oh. Okay, enter item. Again, system event. With the enter item, we send the barcode and the quantity. So if I buy 2 liters of milk, this will be the barcode for milk and the quantity 2. We start a method, enter item, and it ends down here. Within the scope of this method, we create an object of type sale item, put it in a variable called SI. On this object, we set the product ID and we set the quantity. And once we have that, we add it to the current sale. The current sale creates a warehouse just in order to get the information about the object. So this is item descriptions and stuff are in here. We get the description for the milk, might be what farm produced the milk or whatever, and we get the price for the milk, and then we set that price on the sale item, and we increase our total so that we keep a running tally of how much the current total is. And once we're done, we don't need the warehouse object anymore, so we destroy it. And now we have enough information, so we've done what we should, and we can return with the description of the item, and this can be returned to the actor. Right, that was the mechanics of what we read here. A few things to point out here. First of all, creating objects, this is calling the constructor of the sale class, really. So when we say create, we are calling the constructor on a sale object, which means we could put parameters there as well. The destroy, likewise, is the destructor. So the warehouse object doesn't exist after this point. That's why we strike out that lifeline. We can return values in 2 different ways. We can either as here, when I call the method getDescription, and this returns a value that I put into a variable called the description. Same thing with this one. I call the method getPrice. This returns a value that I put into a variable called the price. This variable I can then use later on. So the price is used in the next call, which means that what's returned here is used over here. That's one way of expressing this. The other way of expressing return values is to use a dotted line going the other direction. This is the return value for the method addItem. So addItem returns something, the item description. If I use this format, I can be a bit more loose in how I express it. There is something returned, and I can even write out what is being returned in natural language. But I don't really see where it ends up. With this format, I can say that this is stored in this variable, and then I can use that variable in various ways later on. With this format, all I do is I give a description of what's being returned. This is the format that you would use in a system sequence diagram because it gives you the freedom to express more clearly what is being done, and it matches better with the what is expressed in the use case. When I call create here on the sale item, so this is an object of the type sale item. There's a little colon there on all of these that say that these are objects. The little colon in the beginning of each name says that this is an object of type POS, this is an object of type sale, this is an object of type sale item, and this is an object of type warehouse. This sale item is put into a variable named SI. This variable is then used down here, if you see, where I pass this object or the reference to this object along to the current sale. But I don't know, really, I can't read from the sequence diagram where the variable really is. I can deduce things and I can make an educated guess about things, but I don't really know for sure. So if we start with the sale item here, or the sale object here up here, there's a variable called current. I can guess because this variable is used in, or this object is used both in this use case, or sorry, this object is used in this interaction diagram up here for the start new sale, and it is used in the enter item use interaction diagram. I can guess that it is an attribute of the point of sale class, so that it lives for as long as the object lives. The sale item, since it is only used within the scope of the function enter item, I can sort of guess, and also because the name is it's a really crappy name for an object, I can guess that it is just a variable inside the enter item method. It doesn't even have to be in this method. It could be somewhere else, but it's most likely the method that created the object, and it's most likely in the method that is using the object that this variable is, but it could actually be anywhere else as well. The sequence diagram doesn't specify that, but I can guess, and those guesses will usually suffices to figure out how to build this. What else? I can of course call other methods on the same object. That's what's happening down here. So the sale object inside the scope of the add item method will call the increase total method on the same sale object. So that's of course doable. Anything else? Well, that's about it. Moving on, what I can use this information for is that this will give me all the objects and all the classes I need in order to build these, in this case, these two system events. So if I read from left to right, the top row, I see all the objects that are involved. And for each object, of course, I need a class. So I need a POS class, I need a sale class, I need a sales item class, and I need a warehouse class. Um, so that's the minimum class diagram that I need in order to satisfy these two sequence diagrams. If I read top to bottom, I see all the methods that are required in each class in order to satisfy these interaction diagrams. So the POS class will need to have the start new sale and the enter item methods. Note that the arrow points towards where the method is being declared. So it's the POS class that's going to have the start new sale method and the enter item method. Likewise, the sale class is going to have an add item method and the increase total method. Sales item is going to have the set product ID, set quantity methods, and the set price method down here. So following a lifeline downwards and looking at all the arrows that point towards that lifeline and looking at the names of the methods on them will give me the methods that are required in order to satisfy these sequence diagrams. Which means that if I do interaction diagrams, sequence diagrams for all the system events that I had in one use case, and then I read what classes I need and what methods I need, I have the smallest possible set of classes and methods that I can build in order to satisfy this use case. And that's kind of neat, and I would like to stress that again, that the alternative, which you often see more seasoned software engineers do when they do software design, is that they start with the class diagram and they just list the methods that they think are going to be needed in each class. That usually means that you end up having a few methods more than are actually required. They might not ever be used, but since they're in the class diagram, you will implement them happily, which means that you create a technical depth to yourself. You will need to maintain those methods even though you're actually not going to use them. Likewise, you will have all methods that you think will be required for the system, so that you don't have any way of prioritizing which methods should you start by implementing. If you instead do the sequence diagram route and just extract the smallest possible set of classes and methods, that means that you know exactly that if I build these methods, these classes, I can build this use case and nothing else. The next use case you add might reuse some of the classes and might reuse some of the methods, which means that you only need to focus on the new methods, and then you can slowly extend the system with only the new methods that are required for the next use case. So this enables you to build your system use case by use case in the smallest possible way. And that's good. That's lean and agile, if nothing else. That the arrow points towards the class that should have the method means that I can, when I build this class, I don't really need to worry about who is calling this method. Where is this method call coming from? All I need to know is that I need to have in the sales item class, I need to have the method set product ID. And then it's up to anyone to use it. Same thing with the enter item over here. I'm going to put it into the point of sale class, and I don't really care at this point who is going to call it. Where is this call going to come from? It might come from the user interface. It might come from a test framework, or it might come from some other part of the system that is reusing these parts of the use case in order to enter items through some sort of back-end system. I don't know, and I don't really care, because all I need to do is I need to build it into this class. When I design these sequence diagrams, I will start with the method call. Let's say enter item here. And then I will think to myself, what do I, as a point of sale class, need to do to satisfy the enter item method call? What are my responsibilities? Well, there is such a thing as a running transaction. I know that as a point of sale. I'm not in charge of the actual details of how that is done. All I know is that I need to create a sale item and give it all the information, and then I add it to the running sale. That's my job. Create it because I have the information to create the sale item, and then add it to the running sale because it's not my job to keep track of every sale item I've ever had in this particular sale. That's the current sales job. Once I've done that, is there anything else I need to do? No, I've got the description, I've got the price, which means that I can return, and I will have done my job. I will not worry about what's going to happen in the next lifeline. I will focus on only what's happening inside the point of sale class and the enter item method. I will have blinds on, if you will. I'm not looking at who is calling me, and I'm not looking at what's going to happen with all the other objects involved. Only what is my responsibility to take care of. What should I do, and what should I delegate to others? Do I know whom to delegate it to? And if not, do I know how to figure that out? Then I will take a step over and do the same for the next lifeline. In this case, the sale. Here's the add item method. Okay, what do I need to do in order to build the best possible add item method? I get the sale item. Great. What should I do with that? Well, I need to figure out the description because that's what I'm going to return. I need to figure out the price because I'm going to add that to the total. And I might do a bit of tidying up and remove the warehouse as well, because that's an object that shouldn't be slushing around in the system if no one is using it. And once I'm done with that, I'm able to return the item description, and that's my job done. I don't have to worry about anything else. So I focus on one lifeline at a time, and I skip over, do the next one and the next one. If we look at this sequence diagram, and this is a really long slide, this is more or less half the lecture on this one slide. But if I look at the design of this sequence diagram, who is responsible for what, I am breaking a couple of principles. So I could tidy this up quite a bit and make it a much better object-oriented system. In order to do that, I need to do a brief excursion to the grasp patterns that we will cover in a separate lecture later on. But there are two main principles there that sort of guide how you assign responsibilities to different classes. One is that you have low coupling. You should try to have as few couplings as possible and as loose couplings as possible between the objects and the classes in your design, so that you don't need to know more than is necessary of the world around you in order to do your job. So that's one principle. And the other is high cohesion, and that means that whatever you should have as few and as well-defined responsibilities as possible for each class. So each class should have a well-defined responsibility and shouldn't really do much outside of that responsibility. If it is something that would add responsibility to a class, then maybe you should consider putting it in another class. There's of course a few conflicts going on there between low coupling and high cohesion, but I'll get into those in that lecture. These two principles can also be expressed in more detailed form when we talk about, for example, information, where we say, I talked about that the point of sale system has the information to create a sales item object, and therefore it should do that. That's one of these grasp patterns. It's the creator grasp pattern. whoever has the information should act on the information, and whoever has the ability to act on the information should also have that information. That's called the information expert pattern. Those two will also should also guide the way I build my design. What this means is that I can do a bit of tidying down here in particular. These two look a bit. I could probably get away with putting these two method called set product ID and set quantity. I could throw them in as attributes to or parameters to the constructor here instead. That would remove them for me. But that wouldn't change anything significant in the design. It would just clean up this graph a bit, but it wouldn't change the design as such. It would still be the point of sale system responsible for creating the sales item, and it would still mean that it has to pass along that information in some way or other. But down here, we have a few other things that are going on. Why does the current sale, the sale should be responsible for keeping track of the items that I've added to my sale. That should be its sole responsibility. It shouldn't have to worry about other things. It should know that there's such a thing as a sales item, and it can query the sales item. What's your cost? But it shouldn't have to know how the sales item goes about getting that information. Because that means that it needs to know more about the world around it than is strictly necessary. So what we would like to do is that we would like to make the sales item, as soon as it's got the product ID here, it can actually go and ask the warehouse itself, what am I? I've got this barcode. What's my description? And once you have the quantity, you know the barcode and you know the quantity, then you can go and ask, how much should I cost? With the barcode, I can ask, what is my price from the warehouse? And with the quantity, I can calculate how much this sales item should cost. And that means that the sale doesn't have to set the price, but it can query the price, it can get the price, and it can get the description, but it can do that from the sales item, which means that the total number of connections for the sales object or the sales class will be fewer, because it doesn't need to know about the warehouse, it will only need to know about the sales item. And that tidies things up a bit. This means that I can probably reuse the sales class in other situations where I might have a different type of sales item that gets this information in some other way. And I will, when I do maintenance on the sales object and the sales class, I know that it's just responsible for maintaining a list of sales items and asking them for more information where appropriate. There, continuing the recording now. So I was talking about the making this a better design with the help of a few of the grasp patterns, making sure that the sale class only has to know about the sales item and doesn't need to know about the warehouse. This means that the sales item, of course, needs to know about the warehouse, but it should be responsible for getting the information it needs in order to do its job. It shouldn't sit on its hands and wait for someone else to give it that information. This would empower this object to be more responsible for its own information, more responsible for its own tasks, and it would free that job from this sales class, which can then focus on only listing sales items. I would probably want to remove the connection between the point of sale class and the sales item as well. Why does the point of sale class need to know about the internals of a sale? Really, what I would like to know, so as a point of sale system, I would like to know that I have a current sale going on, and whenever someone enters an item, I can trust that the current sale is able to deal with that somehow. But because as it is structured right now, with that the point of sale class creates the sales item objects over here, that means that the point of sale class needs to know about how the current sale plans on storing each sale item. So I know a bit too much of the internals of the sale class now. So I would probably want to just call the add item with the barcode and the quantity, and then I would leave that to the current sale to create a sale item, if it wants to. It might have another plan for how to do this. It might not want to have one object per sale item. It could be that it stores them directly into a database, for example, or just the text of it, or whatever. That's really up to the sale to decide that. It's not the point of sales job to figure that out. So I would probably want to move these set product ID and set quantity and so on, so that they are done as part of the add item method instead, and that would free up the point of sale, would give it a fewer connections and a more cleanly well-defined responsibility. It would add a bit of responsibility to the sale class, but it would mean that it adds responsibility for keeping track of how it wants to structure its own internals. So it would be a responsibility it should have anyway. Okay, that I think actually is everything I can say at this point for this one slide. Let's take a break there until a quarter past and then continue from there. So I'm pausing the recording now. So, sequence diagrams and communication diagrams, that's another form of what is collectively called interaction diagrams. So interaction diagrams can be either sequence diagrams or communication diagrams. You might also hear the term collaboration diagrams instead of communication diagrams. Or I think older versions of UML called it collaboration diagrams. The key thing here is that they express exactly the same information. This image I have generated using the same source code as the previous one. The only difference is that I have told PlantUML to generate an interaction diagram instead, or a communication diagram instead of a sequence diagram. So they express exactly the same information, but the focus is different. So in the sequence diagram, the focus is that you have a sequence of events that and that objects collaborate with each other in a certain order. So you get the sequence very clearly, that you first of all from left to right, that you first concentrate on one object, and then you concentrate on the next object, and the next, and the next, and the next, and that things happen from top to bottom, that first this happens, then this happens, then this happens, and so on. In a communication diagram, this isn't as clearly expressed, but you can instead focus on which objects are actually collaborating with each other. So in order to read this, you would start to look at the numbering here. So you will look for the 1 over here. This is the first thing that happens. So as enter item starts this communication diagram, what's the first thing that's going to happen inside? Well, we want to create the sales item object. We want to set the product ID and set quantity. Let's go up here. And then we'll have to go hunting around in the communication diagram to find what's the next thing that happens. Well, it's the add item over here. And where's the 5? It's over here. 5, 6, 7. Okay. 8. Where's 8? Okay, it's over here. 9 and 10. So you have the numbering that says in which order things happen. But what you can see instead is, in some sense, how much how much communication there is between different objects. So the current sale and the info warehouse seems to have a lot of communication. There's 4 method calls going on here. In reality, there's 2, and a constructor and a destructor, but it's looks much denser over here. Whereas between the POS and the sale objects, there's just 1 method called add item. So you can get an overview in that sense. Communication diagrams are a bit more dense, so you will often find them in books because they consume only half a page instead of a whole spread of the book, which sequence diagrams sometimes might do. So if you're going to print a book, then maybe you will prefer communication diagrams. If you are working on a design, you're probably working on a whiteboard, and in that case, it doesn't really matter that you spread over the entire whiteboard. It's easier to add a new object, move things around a bit on a whiteboard in a sequence diagram. So I would say that in most cases, I would personally prefer the sequence diagram, but if you prefer this format, then they are equivalent in terms of the information they convey, even though they do convey it with focus on different things. It's good that you can read them at least. If you can read the communication diagrams and the sequence diagrams, then you can both read books and whatever someone has drawn on a whiteboard somewhere. Contracts. Contract used to be a big thing in the UML design world until, well, it still is for some of the UML purists. The idea with a contract is that you try to look at what does the system look like before an event occurs, and how does it look once it's finished. So you will, for the enter item, for example, how does the system look when you start this method call or the system event? Well, there's an object of type sale somewhere in the variable current, and it's got all the previous sale items added to it. So that's the starting point of the enter item system event. And what should the world look like once we are done? So imagine that you have this sale object standing on a stage in all its loneliness, and then you close the curtains and the system event occurs, the enter item occurs, and then when you open the curtains again, what has happened in terms of, are there any new objects there? Well, there's the sale item object. Are there any new relations between objects? Well, the sale has a relation to the sale item object. Are there any attributes that have changed? Well, the total of the total for the sale, how much is how much you've bought for at this stage, that is updated in the sale object. The sale item object has the UPC and the quantity and the description and so on. That has also changed. So all of these things have happened while the curtains were closed. And then this is the very basics of contracts. What did the world look like before the event? What does the world look like after the event in terms of added objects, removed objects, added relationships, removed relationships, changed attributes? Then UML researchers got hold of this and they started adding all sorts of things and saying that you must do these contracts and so on and so on. To me, they are a help. If you don't know how to go about doing the interaction diagrams, well, try to think about what is the contract for this method. What's the preconditions? What's the post conditions? Because that gives you a goal. Whatever happens inside that method should mean that you leave the stage according to whatever goal you set up. So if you know that once the enter item method has been called, you have this new sale item, you have the quantity updated, you have the relationships done, and so on, relationships added. If you know this, then doing the interaction diagrams is just a matter of figuring out how do I go about fixing this so that the end result is whatever I imagined it should be in my contract post conditions. So it's a help for you as a designer, but it's not something that I would suggest that you spend lots and lots and lots of time documenting for every system event, because it doesn't really add that much. It's a help for you to figure out things out, but it's not something that is going to be a vital piece of design documentation. Yes, I think that sums it up. As I said, some UML researchers will want you to spend lots and lots of time on this. I suggest don't do that. It's more important that you actually do the interaction diagrams and focus on them. Right. State diagrams. State diagrams don't really fit into UML, and at the same time they can be really useful for some types of systems. So the idea is that you model the system as a series of states and then events that push you from one state to the next state. So a phone call, if you remember the old classic phones, maybe your grandparents have one of those, where you had, as soon as you lift the receiver, there's a dial tone playing, and then you start dialing the number, and then you talk, and then you hang up. Mobile phones doesn't work; they don't work like this, but the old classic phones did, and that's a phone is a good example of a state machine. We start over here. So this big black ball says that this is where the state diagram starts. We enter some sort of idle state, nothing is happening really, until the event that will lift the receiver happens. As this event happens, we do an action, we play a dial tone, and then we enter the state active. This state is basically what everything else that's going on is in the active state. And then once we're done, we put the receiver down again, and this pushes us back to the idle state. So we focus on what are the states and what are the events that will push me out of this state, and in that case, what state will I then enter? Inside the active state, we have a whole new state machine. We start by entering the state playing dial tone. This is a really bad state, by the way, because this is an action more than anything else. Waiting is probably a better state here. And then I can instead say that underneath this line, I can say that while I'm in this state, play a dial tone. I think I've got an example of that later on. So I'm here waiting, doing nothing really, until someone enters a digit. So I press a digit on the number pad, and then I go into a dialing mode. This means that I'm no longer playing the dial tone, and I am connecting with the telephone switch and saying that this number has been dialed, this number has been dialed. And I can press more digits, and this will just put me back into the dialing state. So any number of digits can be entered here until I have a complete number. That's an event. The number is complete. So I'm now in a connecting state until either I'm timed out, or I give up, or I am connected. If I'm connected, I'm in a state where I can start talking to whoever is at the other end. Until I am done, and I signal that I am done by triggering the event that I put down the receiver. And putting down the receiver pushes me back to the idle state again. I'm no longer in the talking state. I'm no longer connected. This putting down the receiver can be done anywhere in this nested state machine. So as it is waiting for me to start dialing, I can abort and I can put down the receiver there, which pushes me back to the idle state. In the middle of dialing the number, if I realize, for example, that I've dialed the wrong number or the wrong digit, I can put down the receiver, pick it up again, and then start from scratch again. As it is connecting, if I give up on waiting there, I'll put down the receiver, and this will push me back to the idle state again. The problem with these state diagrams is that there's no clear connection to how I'm going to use this information in my future design work. So with all the other UML diagrams, whatever I produce in one diagram is used as input for the next diagram in this chain, so that I will do my use cases, and then I will do my system sequence diagrams based on information from the use cases. Then I will do interaction diagrams based on my system sequence diagrams, and then I will do class diagrams based on my interaction diagrams, and then I will do my implementation based on my class diagrams and interaction diagrams, and so on. In this nice chain, they're all connected. State machines don't fit into this chain in that same sense. So these are more used as an analysis tool in order to understand the systems. Then I will need to express this somehow as interactions and as classes in some other format, but there's no clear one-to-one mapping on how to do that. So they are part of the UML modeling toolbox, but they don't really fit into the unified process as such. But for many systems are state-based, and therefore we have a benefit of expressing state machines like this. And it doesn't have to be on the top level. It doesn't have to be that the whole system changes state. It could be that some parts of some internal part of the system changes states like this. For example, if I want to build a PostScript file, I think PostScript is a state machine. So I would do some form of state machine for just that small part of the system. States are somewhere where the system meaningfully rests for a while. It resides in that state until an event moves you to a different state, and you will have certain actions permissible inside the state. You will have certain activities that are done in that state, and the system will in general behave in a particular way while it is in that state. And when you move to a different state, the system will behave in a different way. So that's a state that a meaningful collection of behaviors for the system that may change based on some event. Skipping this, moving ahead to a state diagram for a Pac-Man game. This was actually a 3D Pac-Man, so you could fall off the map as well. Just as an example. So we start over here, and when everything is loaded, we are entered the state that we are playing. This is the main state for playing Pac-Man. If I hit a candy while I'm walking around on the map, this is the event. I hit candy, and as an action, if this event occurs, I can add to the score. And then I'm back into the playing state. If I meet a ghost, in the normal case, I am no longer playing. I am pushed over to the lost life state. The lost life state is just a placeholder to say that play an animation, you've lost a life, sorry, you now have so and so many lives left. There's an animation that happens while we are in this state, and here we see this syntax that I can do. I can write do, and then whatever should happen while I am in this state. This will continuously happen as I am in this state. I can have entry and I can have exit in the same way. So I can have something that happens no matter how I enter the state. As I enter the state, something particular might happen here. Same thing with exit. No matter how I exit the state, this should happen. If there are more lives, I'm pushed back into the playing state. This, that I don't put an event here, means that when this state is done, whatever that means, then I then I follow this event back to playing. This is a condition within brackets. So here I can qualify the event, saying that there's an event, and if this condition is true, the event should be triggered only if this condition is true. So if we look at the meat ghost, for example, we have the condition that I haven't eaten any of the super candies. If I meet a ghost and I have eaten one of the super candies, well, I follow this event instead. So this condition means that the same event can trigger different parts through my state diagram. If I meet a ghost and I've eaten a super candy, I should just add to the score and go back to playing again. If I fall off the map, I lose a life, and if I don't have any more lives, then I'm done with this entire state diagram. So, good way of expressing things, not as clear-cut how to actually build it. There are a few design patterns, and if you've built any software games, you know a few more that can help you with this, but UML as such leaves you a bit stranded when it comes to actually implementing this. Getting to the class diagram, I've said that. You read from left to right over here. These are the classes, and from top to down, these are the methods. So no point in dallying any further on that. And I think, and I hope that I've answered this by now, that we modeled behavior because we want to know what objects are needed and how should they interact in order to satisfy a particular event. Events are a dynamic behavior as well, of course, so it makes sense that we want to model what's going on inside the system as a response to an event. This will give me the smallest possible system to build, rather than just trying to brainstorm everything that every class should be able to do. That is worth saying, that just as the use case describes one concrete scenario of using the system, the interaction diagrams continue this by describing how should the internals of the system work to satisfy that one concrete scenario. So this is one concrete scenario that I'm trying to express in the interaction diagrams. As I say, it's objects. It's always objects when I describe the dynamic behavior of a system. I will be borrowing the classes and the concepts and so on, and I will convert through the process of you doing sequence diagrams and interaction diagrams. I will get information which enables me to convert relevant parts of my domain model to a class diagram that I then can build a system based on. How far down should I go? I talked about I will be looking at one lifeline at a time, and I will look at what happens in the point of sale class, point of sale object, when I call the enter item method, and I'll move over and I'll do the same for the sale object and the add item method, and move on and move on and move on. When should I stop? Either when there's nothing more to do, like if I set product ID, well, there's nothing more to do than just update that variable and then return. sometimes it's not as clear that I need to that I have a good stop condition, and I think there it could be either when you can hand off to some other system, or when you are reasonably sure that you know how to build whatever is below that point. Again, there's no point in doing design for the sake of doing design. You're doing the same design for the sake of explaining to yourself and your developers how to build a system. And if you're fairly certain that from here on out they know how to build this, well, there's no point in you doing design for the sake of design anymore. But of course, that's not a strict line. It's something that varies depending on the system, on your experience, and on the experience of your developers and so on. Um, so there's no clear line saying that this is how deep you should go and not further. That depends on what you're modeling. And if you're uncertain, well, go down one level more. And that was the last I wanted to say about dynamic behavior and modeling the dynamic behavior of a system.